In the last lecture, we were discussing the features of a turbulent flow. The turbulent flow occurs when the Reynolds number is high. Okay. Typically, the transition to turbulence takes place when the Reynolds number is high. And the turbulent flow is characterized by large velocity fluctuations in all three directions. It is necessarily three-dimensional. At each location, you have velocity. The mean velocity may be only in one direction, but the time fluctuations in the velocity are in all three directions. Transport is primarily due to convection by velocity fluctuations. This mechanism of convection by velocity fluctuations or dispersion is much more efficient than molecular diffusion, and for that reason the flow is highly diffusive and also highly dissipative. And there is a range of length and time scales in a turbulent flow, starting from the largest scale. In a flow in a pipe, for example, the largest turbulence length and time scales will be the pipe diameter and the average flow velocity. Okay. The pipe diameter and the average flow velocity. Okay. Okay. However, there are length and time scales which are much smaller. Why do these small scales occur? Okay. Because the turbulent flow is at high Reynolds number. Okay. And at high Reynolds number, inertial effects are much larger than viscous effects. The dissipation of energy at the small scales has to occur due to viscous effects. So, based upon the large scale velocity and the diameter, since viscous effects are small, the dissipation of energy is not equal to the power input. Okay. Therefore, the flow has to create smaller and smaller scales, such that at the smallest scales the dissipation of energy due to viscosity is comparable to the power that is input at the large scales. The power input is basically the pressure difference times the volumetric flow rate. Okay. Force times the velocity. Okay. Force is pressure into cross sectional area and velocity is flow rate divided by cross sectional area. So, it is just equal to the pressure difference times the volumetric flow rate. We had expressed it in terms of the friction factor and the average velocity. Okay. So, this is the scale, okay. VAV cubed into friction factor by diameter, and I said for a turbulent flow the friction factor does not change appreciably with the Reynolds number. For a laminar flow, we know that the friction factor goes as 1 over the Reynolds number. For the turbulent flow, if you recall from the Moody plot, the friction factor varies very little with Reynolds number. And if we assume that there is no variation of the friction factor with Reynolds number, the estimate for the energy input per unit mass per unit time, or the power input per unit mass, is V average cubed divided by the pipe diameter, has dimensions of length square T power minus 3. Note that power has dimensions of mass length square divided by T cubed. Therefore, the power per unit mass has length square per unit time. This power that is input at the large scales has to necessarily be dissipated. Therefore, the energy dissipation rate per unit mass epsilon is equal to the power input per unit mass, which also scales as V average cubed by D. I had said that the flow at the large scales is anisotropic, that is, the velocity fluctuations at the large scale in the three different directions are different in general. Okay. The velocity fluctuations in the streamwise direction will typically be much larger than that in the cross stream directions. So, it is anisotropic. The smallest scales are so much smaller than the large scales, and the velocity scale is so much smaller than the average velocity, such that the dynamics of the smallest scale eddies does not directly depend upon the average velocity and the diameter. It can be derived only from the consideration that the energy dissipation rate has to be equal to the power input per unit mass at the large scale. Okay. The small scales have to dissipate all the energy, otherwise you will not have a steady flow, the flow will continually accelerate. Therefore, the smallest eddies have to dissipate all of the energy that is put in at the large scale. The size, the time scale and the velocity scale of the smallest eddies will depend only upon this energy dissipation rate per unit mass that I have called epsilon, as well as the mechanism of dissipation, that is the viscosity, or alternatively the momentum diffusivity. This is what will dissipate energy at the small scales. Therefore, the length, velocity and time scales of the smallest scale eddies depend only upon the energy input per unit mass or the energy dissipation rate per unit mass and the kinematic viscosity. Okay. So, two dimensional parameters, okay, and two dimensions. So, therefore, you can create only one length dimension, one time dimension and one velocity dimension from these. Okay. The Kolmogorov scale length scale is nu cubed by epsilon power 1/4, okay, just from dimensional analysis as I had showed you earlier. The time scale is nu by epsilon power half. Okay. You can verify that it has the same dimension as time as I showed you earlier. The velocity scale is nu times epsilon power 1/4. It has the same dimension as velocity. The ratio smallest scale eddies length divided by the pipe diameter is proportional to Re power minus 1/4. Okay. We had done that calculation in the last lecture. Okay. Just substitute for epsilon nu cubed epsilon, you substitute V average cubed by d. Okay. This goes as Re power minus 3/4. The time scale goes as Re power minus half, the time scale divided by the time of the smallest eddies. Okay. It goes as Re power minus half. And the Kolmogorov velocity divided by the average velocity, it goes as Re power minus 1/4. Okay. Note that in all of these cases the Reynolds number is large. I had said the characteristic of turbulent flow is that it is at high Reynolds number. Therefore, the Kolmogorov length scale is Re power minus 3/4 times the pipe diameter. The time scale is Re power minus half the pipe diameter and the velocity is Re power minus 1/4 the pipe diameter. Okay. What is the Reynolds number based upon the Kolmogorov scale? The Reynolds number based upon the large scale we know has to be large, because that is the characteristic of turbulent flows. The Reynolds number based upon the Kolmogorov scale is Lk Vk by nu. Okay. Velocity divided by length scale divided by the kinematic viscosity, okay, which is equal to nu cubed by epsilon power 1/4, okay, into nu epsilon power 1/4, okay, divided by the kinematic viscosity. And you can see that this is 1. Okay. So, the picture of turbulent flow is as follows. Okay. The Reynolds number based upon the large scale velocity is much larger than 1, okay, high Reynolds number. The largest eddies, the Reynolds number is large compared to 1, which means that inertial effects are much larger than viscous effects. Since the energy that is put in at the large scale has to be dissipated at the small scale, this implies that for the large scale flow, the energy dissipation rate is much smaller than the rate of input of energy. However, the flow creates smaller and smaller scales in such a way that at the smallest scales, the Reynolds number is order 1, and therefore, the energy dissipated is comparable to the energy that is put in at the large scales, okay, and thereby all of the energy is dissipated due to the creation of these small eddies. Okay. Let me summarize this for you. Okay. and I will write these for the flow and the Kolmogorov scales. Okay. Okay. And then I also write the ratio, okay, of these two. Okay. And the ratio. Okay. Quantity is the length, it has dimensions L. Okay, and then the ratio. Okay. The flow scale is of course the diameter. Okay. The Kolmogorov scale Lk is equal to nu cubed by epsilon power 1/4. That is what we had derived by dimensional analysis. The ratio is R e power minus 3/4. Okay. Flow to Kolmogorov scale. Okay. Velocity L T inverse, average velocity Vk is equal to nu epsilon power 1/4. The ratio is R e power minus 1/4. Okay. That is what we had just derived. Okay. Time, dimension t, this is d by V average, length by velocity. Okay. Tk is equal to nu by epsilon power half. Okay. And the ratio is R e power minus half. Okay. So, the ratio of the Kolmogorov to the flow scale is much smaller than 1 for the length, velocity and time scales. Strain rate has dimensions of T inverse. Okay, for the large scale, this is the inverse of this, the ratio of the velocity and the diameter. And the strain rate for the Kolmogorov scale is going to be equal to Vk by Lk. Okay. And this, if you work it out, will be epsilon by nu power half. The ratio of these is the inverse of the ratio of the time scales. Okay. Strain rate has the inverse dimension of time, therefore, this is going to be equal to R e power half. Okay. So, therefore, the strain rate in the smaller scales is actually much larger than the strain rate in the large scales. Okay. The strain rate in the large scales is V average by d. Strain rate in the small scales is much larger, it is R e power plus half times the strain rate in the large scales. Okay. The Reynolds number is dimensionless, this is V average d by nu. This is Vk Lk by nu, which we just calculated was 1. Okay. Therefore, the ratio of these is just Re. Okay. The Reynolds number for the large scale flow is the flow Reynolds number. Reynolds number for the Kolmogorov scale is just 1, okay, because it is only if the Reynolds number is 1 that the energy dissipation rate at the small scales will be equal to the power input per unit mass at the large scales. Okay. What is the kinetic energy? Per unit mass. Kinetic energy is mass times the velocity square. Kinetic energy per unit mass will be just the velocity square. Okay. L square t power minus 2. Okay. This kinetic energy per unit mass is just the average velocity square in the large scales. In the small scales, it is the Kolmogorov velocity square. Okay. average Kolmogorov velocity by the average velocity is equal to r e power minus 1/4. That means that this is equal to r e power minus half. Therefore, the energy in the small scales is much smaller than the energy in the large scales. Okay. The energy in the small scales is much larger than the energy in the large scales. Okay. The power input per unit mass. This has to be the same for the large scales and the small scales, okay, L square t power minus 3. Okay. This has to be the same because I said that at steady state whatever power is input per unit mass has to be dissipated. The power dissipation rate per unit mass at the small scales has to be equal to the power input rate per unit mass at the large scales. Okay. And the dissipation rate per unit mass, okay. It has dimensions of length square t power minus 3. Okay. This is equal to nu VAV cubed by sorry. Recall that we had said that the dissipation of energy, okay, is equal to mu into dVx by dz the whole square. Okay, that is the rate of dissipation of energy. Okay. Or if I want to calculate the rate of energy dissipation per unit mass, okay, that would be the kinematic viscosity times dVx by dz the whole square. Okay. This is the rate of energy dissipation per unit volume. Okay, we had derived this earlier. The rate of energy dissipation per unit volume is the shear stress times the strain rate. Shear stress is mu into dVx by dz and the strain rate is dVx by dz. So, you multiply the two, you will get the energy dissipation rate per unit volume as mu into dVx by dz the whole square. Per unit mass divide by the density. Okay. Energy dissipation rate per unit volume divided by density will give you the energy dissipation rate per unit mass is equal to nu into dVx by dz the whole square, which will scale as nu into V average square divided by d square, okay, for this case. Okay. For the Kolmogorov scale, this is equal to nu into Vk square by Lk square. Okay. And this has to be equal to epsilon, right, because energy put in has to be dissipated. Okay. The ratio of these two is going to be equal to Vk square by Lk square into d square by V average square. Is the square of the strain rate. Strain rate goes as r e power half, therefore, this will go as r e. Okay. So, therefore, the rate of dissipation of energy in the small scale divided by the rate of dissipation of energy in the large scale is r e, okay, which is much larger than 1 for a high Reynolds number flow. Therefore, even though most of the kinetic energy is in the large scales, most of the dissipation takes place at the smallest scales in the flow. Okay. So, energy is put in at the large scale due to the pressure difference across the pipe and the volumetric flow rate. That energy is transferred by eddies of different sizes until at the smallest scales, okay, that energy gets dissipated. Okay. So, that is what is called the turbulence cascade. Okay. So, you have a series of eddies, okay, all the way from larger scales have diameter d, smaller scales have Kolmogorov scale. Okay. The energy is pumped in at that large scale, okay, due to the pressure difference that is applied across the length of the pipe. That pressure difference is applied across the entire cross section. Therefore, the length scale for the energy put in is at the largest scales. That energy gets transported due to smaller and smaller scale eddies. Okay. At the large scales, the rate of dissipation of energy is much smaller than the rate of energy input, because the Reynolds number is much larger than 1. The flow itself creates smaller and smaller scales, such that at the smallest scale, the Kolmogorov scale, the Reynolds number is order 1. The rate of energy dissipation is comparable to what is put in at the large scale, and therefore, you have energy dissipated at these smaller scales. Okay. So, this is what is called the turbulence cascade. Okay. This is what is called the turbulence cascade. Okay. Okay. So, that is a picture of a turbulent flow. At the larger scales, the Reynolds number is large, the rate of dissipation of energy is small. Okay. The energy is transported through smaller and smaller scales, until at the smallest scale, the energy dissipation is comparable to the energy that is put in at the large scales. This energy dissipation that takes place at the smallest Kolmogorov scales. Okay. I said that the that Lk, okay, goes as R e power minus 3 by 4 times the diameter of the pipe. These smaller scales are still much larger than the molecular scales. You recall I told you one of the characteristics of turbulence is that the smallest scales have a size and a velocity that is much larger than the molecular size and the molecular fluctuating velocity, okay, for incompressible flows. Okay. So, let us solve a problem where we estimate the ratio of the Kolmogorov scale and the microscopic scale for a turbulent flow of a gas. Okay. Note that for a turbulent flow of a gas, the microscopic scale is the mean free path. Okay. Of a gas. Okay. The molecular length is equal to the mean free path lambda, okay, and the molecular velocity is equal to Vrms, the velocity of the molecules, of the gas molecules. Okay. Which, if you recall, this was equal to square root of 3 kb T by m. Okay. This was equal to 1 by pi n d molecular square, the whole inverse, okay, where n was the number density of the molecules. Okay. And the kinematic viscosity is proportional to lambda times Vrms, to within a multiplicative constant. Okay. So, I will just write it as proportional to rather than approximately equal to. So, what is the ratio of the Kolmogorov scale divided by the mean free path? Okay. This is equal to Lk by lambda. Lk, recall, was equal to nu cubed by epsilon power 1/4 times 1 by lambda. Note that the kinematic viscosity is Vrms cubed, okay, times lambda cubed. Vrms cubed lambda cubed power 1/4, okay. That is nu cubed power 1/4. Epsilon is V average cubed by d whole power 1/4, okay, into 1 by lambda. Okay. So, this you can easily verify is Vrms by V average power 3 by 4, okay, into d by lambda power 1/4. Okay. Vrms by V average. Okay. Note that the Mach number is equal to, or rather it is proportional to V average by C by Vrms. Is the ratio of the flow velocity and the speed of sound. Okay. Is the ratio of the flow velocity and the speed of sound. Okay. Therefore, I can also write this as, okay, this is equal to 1 by Mach number to the 3/4, okay, into d by lambda. Recall that lambda by d is a Knudsen number. Okay. Lambda by d is a Knudsen number, the ratio of the mean free path to the macroscopic scale. Okay. Okay. And also the Knudsen number is equal to d by lambda, sorry, lambda by d. Okay. Okay. I can write this, the Knudsen number, in terms of the Reynolds number and the Mach number. Okay. I can write this in terms of the Reynolds number and the Mach number. This will be equal to the Mach by the Reynolds, okay, for a gas. Okay. Okay. We had derived this earlier and I will briefly show you how that comes about. Recall that the Mach number, okay, so if I take Reynolds number, okay, Mach number is V average by Vrms into the Reynolds number is nu by d Vrms. Okay. So, this is equal to V average by Vrms, and kinematic viscosity is Vrms lambda by, okay, d Vrms. I am sorry, the Reynolds number is based upon the average flow velocity. So, this is the average. Okay. Okay. So, this is the same as lambda by d. Okay. This is the same as lambda by d. Okay. These I should put approximately equal to, these are not exact, okay, because there are multiplicative constants there in the expression for the kinematic viscosity. Kinematic viscosity is not exactly this, there are multiplicative constants, but it is of that order of magnitude. Okay. So, if I substitute for the Knudsen number here, I will get 1 by ma power 3/4, okay, into Re by ma power 1/4. is equal to Reynolds number per 1/4 by Mach number. Okay. So, that is the ratio of the Kolmogorov scale and the mean free path. Incompressible flow, Mach number is small compared to 1. High Reynolds number flow, Reynolds number is large compared to 1, which implies that for a high Reynolds number incompressible flow, this is always much larger than 1, okay, for a gas. Okay. For a liquid, the length scale is smaller still, so you would expect that the ratio would be larger still. Okay. And you can do the same calculation for the time scale. Okay. The time scale for the Kolmogorov scale divided by the time scale for the gas molecules, which is lambda by VRMS. Okay. Kolmogorov scale, time scale is nu by epsilon power half, okay, divided by lambda by VRMS. Okay. And you can do the calculation in exactly the same way, and this will turn out to be equal to Re power half by Mach number square. Okay. High Reynolds number is large compared to 1, incompressible Mach number is small compared to 1. So, once again we find that this is much larger than 1. Okay. Therefore, both the length and the time scales for the Kolmogorov scales are much larger than the molecular length and time scales, the mean free path and the ratio of the mean free path and the velocity, RMS velocity. Therefore, these length, the Kolmogorov length and time scales are much larger than the molecular length and time scales, and therefore, the continuum approximation is valid for the Kolmogorov scales. The Kolmogorov scales, the dynamics at the Kolmogorov scales is a continuum phenomenon. All the turbulent scales at high Reynolds number and low Mach number can be determined just from the continuum equations themselves. Okay, you do not have to actually calculate and go to the molecular scales. All of these, so this proves that turbulence is a continuum phenomenon. So, I have described for you briefly the characteristics of turbulence. Next class, we will look at some of the characteristics of turbulence in a pipe flow. I will continue this in the next lecture. I will see you then.